Hi, everyone. Welcome to Build. My name is Doris, and I'm joined by my colleague Vinay today. In this session, we'll walk you through how you can build and train an end to end machine learning model right inside of Snowflake. So let's start by first looking at an overview of an end to end machine learning workflow. So imagine you have your data in Snowflake. We can perform data pre-processing and feature engineering, turning raw data into something that's ready for model training. And then we can train our machine learning model using the featureized data that has been captured in our feature store. So this keeps all of our features organized, governed, and consistent across training and inference. So you're not having to reinvent the wheel each time. Once our model is trained, it is logged into the Snowflake model registry, and from there, it's ready to be used for inference so that our predictions can flow right back into your application or analytics. Now, as our data grows, we start to hit some of the limitations with this workflow. In particular, this shows up in two different points in this workflow. First, when we're doing data preparation or transformation, things can really slow down or even fail as we run into memory constraints on large data sets. Similarly, as we move into model training and hyperparameter tuning, these stages also become increasingly resource intensive and less efficient. So, at the larger data scale, we need to rethink how we handle these steps. For example, how we can potentially leverage distributed compute by pushing more of the heavy lifting into Snowflake. And so in this talk, we're going to take a look at two ways of eliminating these bottlenecks. First is for data transformation and feature engineering. We'll introduce Pandas on Snowflake, which lets you build your Pandas pipeline directly in Snowflake at any scale. It makes it easy for you to move seamlessly from prototyping to production without worrying about data sizes or memory limits. Next, for model training and tuning, we'll take a look at Snowflake's machine learning distributed training APIs, which will let you train your ML models and run hyperparameter tuning across multiple cores and GPUs in your Snowflake cluster. In other words, you can scale up your training workloads without ever having to leave Snowflake. So let's start with the first step in this process. Now, Pandas is one of the most commonly used libraries for data transformation and feature engineering. And with Pandas on Snowflake, we're bringing that same familiar experience with Pandas directly into your Snowflake environment to combine the ease of use of Pandas with the power and scalability of Snowflake. You can work with your Snowflake tables or files just like you would with Pandas, but as your data grows, your code automatically scales so that your pipeline stays fast and efficient and production ready. Now, the way that we actually do this underneath the hood is that users would go ahead and write some pandas query. And let's say in this case, pd.concat, which essentially takes two data frames and combines them horizontally. And then we take this pandas query that is written in Python, translate that and essentially push that down to SQL to run on the Snowflake engine. What that means is that your data never has to go to the client side and you never run into these out of memory issues because your client side memory is not big enough. Instead, we push all of this down to the Snowflake engine so that it can run scalably with Snowflake. We're also really excited to announce a new update to Pandas on Snowflake, which is hybrid execution. This is a significant step forward in supporting Pandas pipeline at any scale. With hybrid execution, Snowflake intelligently determines whether to run your Pandas code locally using standard in-memory Pandas or to push it down to the Snowflake engine for scalable execution. So this means that developers can continue to write their familiar Pandas code, develop these robust pipelines without ever having to think about what's the most optimal or efficient way to run your code. And being able to benefit from Snowflake's performance and scalability as your pipelines scale. Here you can see some of the benchmark comparisons on representative workloads showing that Pandas on Snowflake can scale up to a terabyte of data, even in cases where Pandas completely run out of memory. And even when you're looking at the smaller data scale that does fit into memory, for example, this around 10 gigabyte scale, we've also been able to show up to 30x faster performance compared to standard in-memory Pandas. Okay, so we've now taken a look at how you can accelerate your feature engineering and data transformation with Pandas on Snowflake. Next, I'll hand it over to Vinay, who will share more about our Snowflake ML offering.
Thanks, Doris. So yes, so in this section, I'm going to be presenting around Snowflake ML, and we'll see how the end-to-end journey, starting with Pandas and Snowflake, leads into Snowflake ML, and how we can use the capabilities in this platform to build an end-to-end ML pipeline that can scale across any size of data. So Snowflake ML provides a tightly integrated set of capabilities. So you have flexibility in packages and infrastructure. It's highly scalable. It can work with large quantities of data, can work with complex architectures, and at the same time is cost efficient for you to build and operationalize ML, all within the confines of a governed, secure Snowflake environment. So just to maybe expand a little bit more on what I said. So when we meant flexible, users can pick from a wide variety of pre-installed, pre-built, and pre-configured environments and packages. But the flexibility comes in being able to select, install your own packages, bringing your own private repositories or public repositories. If you want to bring in custom models, bring in your own additional frameworks that you want to train against. So that type of flexibility exists where we let you pick your developer tooling of choice, but give you this infrastructure and the data access where you can scale those workloads out directly over where your data lives. Now, especially when you're trying to train on complex model architectures, you're building large scale deep learning models, or you're training classic ML models on very large volumes of data. So that's where the scalability of the platform shines. And we have um, infrastructure choice of a wide variety of node types. You can check, you can pick CPU variants and GPU variants and varied size of memory and other resource capabilities. All of this is fully managed by Snowflake. So you as a user do not have to have any infrastructure setup skills to utilize this platform for running such large scale workloads. And with container runtime, which we'll touch on a little bit, you have a specialized environment for ML where you can get started either directly on notebooks or any other IDE and take advantage of the scalability we offer in the form of APIs, which cover a wide variety of ML and data processing frameworks that not just gives you a great performance benefit, but at the same time is also cost performant. And we'll take a quick look at some of this data. So we consistently run benchmarks. So we want to make sure that we're not just giving you a good scalable platform, but we're giving you what we perceive as the best scalable platform. We want to make sure that our training algorithms perform efficiently, give you the best GPU performance, is working really well on both the bringing data in and also operating on the data across multiple nodes. So across many other platforms, we run benchmarks and we consistently see orders of magnitude performance improvements, both on an end-to-end runtime. And as you can see, given we run on container services where the infrastructure is so competitively priced, the same performance benefit you see in this left chart on end-to-end runtime translates into cost performance benefit. So overall, it's scalable and cost effective. So let's, I again touched on this really briefly. This is the container runtime environment. So we'll take a look at what is powering all the scalability and flexibility that we just spoke of. So again, the container runtime is a pre-built environment. It is packaged with open source libraries, open source frameworks, most of what you would need for any ML development workflow. It includes pre-processing and feature engineering libraries, training libraries, data visualization, data quality checks and ML quality checks, and many others. And of course, if you do want to pip install your own, you want to point to a private repository where you have a research set of packages that you want to leverage in addition to the ones we include, or you simply want to go into the public space or public domain where you want to get access to a long tail package or something really bespoke or a particular version. All of this is fully capable through this extensible container runtime environment. Now, beyond the fact that it's a pre-built environment, this container runtime environment, each time you spin up a notebook or any of our ML job infrastructure capabilities, uh, also comes equipped with a ray cluster. So the ray cluster is an ephemeral ray cluster that one users can use for scaling out their data engineering and data processing tasks, as well as, of course, in this case, ML specific tasks themselves. But we, as part of the Snowflake ML platform, have built certain APIs that are over this ray cluster that make a lot of these common data processing and ML tasks a lot simpler. So for one, you can use data acceleration. So the framework is called Data Connector, which is a set of tools that accelerates data loading wherever the data is. So if you happen to have large amounts of data in Snowflake tables, or this is data as unstructured data, likely stored as images or PDFs or text, wherever they are in S3 buckets and any other cloud providers. That's We give you an accelerated data loading framework, so you can bring in these structured and unstructured data into the memory of the environment where you're operating in, so you can take advantage of all these libraries that we spoke of to perform accelerated um, end-to-end data processing and model training. So once we have the data loading, we also have a set of APIs for distributed ML training and hyperparameter tuning. So think of XGBoost, LightGBM, PyTorch, and so on, as well as hyperparameter tuning APIs for any such training library themselves. We also have newer frameworks. So one of them is called the many model framework, which effectively scales out training across hundreds, thousands of partitions of data, and at the same time also helps you to run inference on the same partition model. And if you want to extend training to general data processing, again on a per partition basis, the framework is also capable of that. All of these operate on the ray cluster, so that you get the benefits of efficient scheduling, optimized use of resources that the ray cluster is designed really well for. All of these operate on GPUs or CPU clusters, and as we spoke earlier, the setting up and configuration of these instance types is abstracted away for you. So it's as easy as opening a notebook where this entire environment is available and is up and running, and you can just simply select the type of compute pool you want and then get going with this large scale ML development. So just a quick double click into one of these areas. So we have a way to optimize data ingestion. So earlier we spoke of how you can use Pandas to do a lot of the early stage data processing, data transformation. But once you bring that into the ML workflow, the ML pipeline, there are opportunities for you to also apply large scale data transformations, say on feature engineering, feature selection, and so on. So some of that is empowered by uh, ingesting these large data sets that are more predominant when you're looking to build a production ready model. So with Snowflake's data loading APIs, users can see up to, we've seen benchmarks where we've seen up to 10 times faster data loading as compared to open source frameworks. And as you grow the data set sizes, you can see more scaling proportional to the size of the data. Now the data has been ingested. Let's look at the training area for a little bit. So the Snowflake's distributed training APIs cover both traditional ML and deep learning models. And with our APIs and the benchmarks we've run, we've seen that users can speed up their training by orders of magnitude, sometimes 3 to 7 times faster compared to what we've seen for open source. Again, for the dataset sizes we've tested. So in this case, as you can see in the chart above, um, 20 to 25 gigabytes of data for a data set in memory, we were able to see significant speed up. But we've seen in reality, data set sizes can be much larger, tens, hundreds of times larger. And the scalability translates as the data set sizes get larger. Great. So we've seen how the platform is set up for you to succeed in operating on such large data and performing complex transformations. Now let's take a look at some of these frameworks in action in a demo that we have set up for you inside a notebook. The overall workflow is exactly like we called out. We'll show you how an efficient ML development pipeline looks like, starting with Pandas and Snowflake and leading into the distributed framework that we have to offer in Snowflake ML. So at a high level, what you will see here, we'll make sure that the infrastructure and the resources are in place. So for this exercise, we plan to use 4 NVIDIA GPUs as part of this notebook, and we'll see how that is used to scale out the ML processing. And we'll start with data from a Snowflake table and the extraction of the data and using it to run some of the early stage transformation and pre-processing is what we will use Pandas and Snowflake for. And we then do a handoff for how that leads to a training approach. And we'll look at a few different variants. We'll start with open source just to show the baseline, and we'll paint the art of the possible with a distributed XGBoost approach. Note that this is a demo, so the dataset sizes are going to be small, so you're not going to see the scale that you'd expect with distribution. But when you get to larger datasets, that's where you're going to see the biggest bang for your buck. We'll close out with showing you how to then take this forward post the notebook, how to operationalize this workflow. So starting with the Snowflake model registry, how that can then set you up to deploy these models into production. Great. So first thing, as we already called out in the slides, the notebook, when you start up, comes with this predefined environment. So as you can see, even if I'm trying to pip install something, there's a lot of packages already included. And of course, as we said, if you do want to include a package that is not included or a particular version that is not supported, you can do that. And that's what we demonstrated. Great. So we have that installed. I will import a few packages, and here's where we want to call a few things out. So we will import pandas, and that is what we're going to use to show some of the baseline, like if I just bring it into memory, how it performs. And these are the imports that we are doing for Pandas and Snowflake, which does the distributed pandas that gets pushed down and materialized inside a cluster of warehouses. Cool. So now that's installed. We have our environment set up. And let's take a quick look, as we said, for what infrastructure we're running on. We are so we have picked a GPU runtime of the image, so that is in the notebook setting. So as we see here, it's a GPU version of the notebook. And so that comes with GPU packages, CUDA packages, as well as part of the image, and that helps me discover things like the types of GPUs and other properties of the GPU. In this case, we have established that okay, there are 4 GPUs. Again, this is on one node. You can discover them if you have multiple nodes, but for this demo purposes, it's 4 GPUs on this node. Cool. So first things, let's go look at an approach for how you can bring data in and do this pre-processing like we described. So of course, you can go point to a Snowflake table, bring it into memory in Pandas with the two Pandas call. And in this case, I'm just printing the shape of the data, which is 400K rows. So this is a typical approach for what you would do by trying to bring it into a two Pandas frame and then running processing. This takes about 10 seconds. Of course, the data is small. As the data gets larger, you are probably paying the penalty of loading the data every time. Now, this other approach of using the distributed pandas or the pandas in Snowflake actually pushes the compute down. So you can clearly see that the benefit is a lot higher. It's a lot quicker. And this, of course, scales as you try to do more complex tasks. Great. So now that I have a pattern in which I want to run this type of data transformation, I can do some really basic steps. So in this case, I'm just doing some basic data cleaning, dropping a few columns, populating nulls with NAs. So again, standard stuff. So also maybe a rudimentary dimensionality reduction step, of course, all using just a simple pandas process. And where I want to do things a little bit more involved, like one-hot encoding, we can see where, yeah, well, this is a very basic one-hot encoding method supported in the modern pandas framework. And this is going to push the compute down into the warehouse on this large, this reasonably sized data set. This should take a small amount of time to complete. But as we've established, when the dataset sizes get much larger, trying to bring this into memory again, running one hot encoding on it on likely a scikit-learn package can be more expensive. So for simpler tasks like this, it's much easier for you to simply push the compute down. So So far, we've seen there's a lot of options for you to use standard Pandas transformations. So the learning curve is the same. You are still using Pandas, but everything is going to get pushed down, materialized where the data already is, closer to the storage of the data in the warehouses where it's getting computed. And because of the scalable distributed framework that is backing this Pandas on Snowflake, you can run scale out operations as well for much larger data that would otherwise not fit in memory. All right. So now that we have some degree of data transformation done, you are possibly going to save this to a table, and then you want to then run some sort of ML workflow over it. So let's sort of hand off or transition into this ML sequence. So first things first, we are doing a typical train test split. And in this case, we're loading the data back into memory. This is purely because we want to run some open source based training, training and fit functions. And we'll see in a bit how that itself is optional if you're using a distributed API where we can read directly from a table and you don't have to bring the data into memory. Great. So as part of the training step, we look at a few things. We look at the open source variants, both CPU based and a GPU based variant of the XGBoost. And as we execute it, we will kind of see how they differ, and then we get into the distributed approach, which we'll spend some time on. So cool. So the open source one with purely just a CPU version, we'll see how, and you can already see it's running on a CPU. We can see that there is a fair degree of CPU consumption, because this is obviously running purely in memory and in a CPU. And once this completes, this should take about 20 to 30 seconds. We'll see how this can be a lot quicker by running on a GPU. Note that the GPU again is an A10 GPU, and also the dataset sizes are really small. So the benefit of using a GPU is a lot stronger when you're dealing with larger data. But you should still see an acceleration. It should still be a lot quicker than what you see with the CPU. But of course, as you know, the value is in much larger data. So similarly, we have the resource monitor here, where we can also see per GPU usage. So one thing to note, you can see there are 4 different GPUs, reflecting the fact that this notebook instance is running on 4 GPUs. But this one particular fit function happened on one of the GPUs, and we can see that that GPU spiked for a short duration, reflecting of course the small data set on which we've trained. So great. So this took about 19 seconds, clear acceleration compared to CPU, but of course these are still in the realm of seconds. You'd still see much larger benefit when the data sets are even larger. And that's what we'll get into in showing how we can do this on a distributed API. So first things first, let's clean up some GPU memory so we give more for our distributed trainers to run with. And before we train, let's examine a few things. The first thing to call out is the GPU scaling config. Actually, let's fire this off first. So the GPU scaling config is how you define how much you want to scale your training operation by. So here we have one node, and you have, let's say I'm using 4 workers, and I've set to use GPU, which means now I've got, as we saw earlier, we have 4 GPUs. So you're going to have 1 worker per GPU. And that's how we get the entire cluster node being used. If I have multiple nodes, where let's say I have 4 nodes and I have the same config, which is 16 GPUs, I can set this to num worker 16, use GPU true, which means I'm going to have 16 concurrent workers all training on GPUs in parallel. Note that the rest of the call is very simple. It is the same exact definition that we did above. You set the tree method and the estimators for the XGB fit operation, and all you do is pass in the extra scaling configuration we specified above. When you kick this off, there's a few things that we display in the notebook for you. There's a lot of information, and you can see that Ray is being invoked quite actively here. A Ray actor is set up for each of these workers that's been instantiated. The data conversion happens to a Ray dataset automatically, so Ray can interpret and run this in a distributed manner. And what we also include is a training progress bar. So as we saw earlier, we set the number of estimators to be 2000. So you can kind of see how we're converging towards that goal, and each boosting round is updated for each training iteration. Other things to note here, interesting facts, you see that because we're running on 4 GPUs, as you saw, there were 4 workers and 4 GPUs, you can see all 4 being used. Of course, the data set sizes are small. It's as it is 400K records and just a small set of features. So distributed across 4 GPUs, you're leaving a lot of GPU underutilized, and GPU memory is fairly less utilized. But the message and what we want to convey to you is, when you want to get to really large data sets where you want the benefit of distributing across GPUs, where in-memory operations or single-threaded operations are insufficient, this is the method that we would recommend. Cool. So again, as with earlier, you can track this in our resource monitor. So we'll see how. So this one's a little lagged behind the live monitor. This gives you more up to date live information, but we'll see in a bit how you'll also see GPU utilization here. Let's come back to that. So before we get there, just maybe one more thing to call out here. Um, as we saw earlier, this dataset was brought into memory, so it's effectively just a pandas data frame that we're passing into the distributor. But when you actually want to operate on datasets much larger, you would use a data connector framework, which we will point you to once we in the quick starts that is in the slide deck, where the data is read directly from Snowflake tables and passed into array dataset, and it does not need to be brought into memory. Great. So the training seems to be completed. We can kind of see with the GPU usage, there was a minimal GPU spike. But again, that reflects the fact that the dataset sizes were small. And once the model has been trained, you can then, so the booster, the model that comes out of this is just an open source construct that you can easily log to into our model registry and infer on this with even a CPU and so on. So in this case, just take a quick look. The model, we simply have to instantiate a model registry and call a log model. And again, you can decide to host this as a service, in which case you would log this with a parameter to be hosted as in a SPCS, or you can also have this hosted in the warehouse where it can be triggered in a batch form closer to where the data is. This is a quick start that you can follow along at any time. This is the demo. The notebook we walk you through is based on the quick start that you see here. It walks you through a little bit more in detail on how to also take this model further. You can also see hyperparameter tuning in this notebook, as well as deploying this model and even monitoring it. And for those who want to learn more about Snowflake ML, please visit snowflake.com/ML.